an enormous range of topics, but all centered around physical chemistry and spectroscopy and the behavior of molecules. I'll say when they are perturbed but even for somebody like me who does condensed phase spectroscopy and worries about how things behave beyond linear response, there's a lot of insight from Bob over a great many years. I actually met Bob the year before, 2 years before I came here. So back in 1980, I met him because in my last year of graduate school, I had applied to MIT, and Bob was visiting Stanford, where I was a student, and wanted to decide whether to invite him. And I remember we must have eaten lunch. We had lunch, Bob and I, and my research advisor, Mike Fair. And it wasn't just some simple cafeteria. And the reason I remember that so clearly is because the first thing that happened was to sit down, I had a plate or something, and I dropped a sandwich right over Bob's lap. So it was a great start. But somehow I was able to snatch both pieces as they separated out of the air before they actually landed on his lap. And this impressed him so much that he did tell them to invite me. Just to put that into a little bit of perspective. So Bob looked probably a little more like this back then when I met him. But if you compare that to how I looked at the time, you could easily guess which of us more closely resembles our earlier self. That's pretty clear. But Bob really has had this enormous impact throughout physical chemistry, and he's been recognized in myriad ways. I'm not going to go recite them all, and he wouldn't want me to recite them all, but most of the awards that molecular spectroscopists could be recognized with, by our favorite societies and institutions and National Academy and elsewhere he's received. But I think more than that, it's really the content, right? That's where he's just had this profound influence on so much of physical chemistry. And really, a couple of generations of physical chemists have been influenced by Bob and have been, unbelievably impressed by the innovations that he's brought to spectroscopy in so many ways. Just to indicate how wide his influence goes, even an innocent condensed phase spectroscopist like me is actually collaborating with Bob, right? And just to show you how much influence he's had and how little in the other direction. It's not like we're collaborating on condensed phase, ferroelectric phase transitions. No, we're collaborating on gas phase molecular rotational spectroscopy, right? Because it's Bob. And so, even among many people who aren't your straight up gas phase spectroscopists and that class of physical chemists, Bob has just had an extremely wide-ranging impact on really the entire field. So it's a pleasure to be able to introduce him now, and I'll bring him up to start his talk on broken patterns of broken atoms.
Thank you, Pete. I don't remember the sandwich incident. Probably even forgot before we invited you. Okay.
What second? Sorry, it's not a shared room yet.
His talk follows directly from that. There's no need to change it.
Yeah, but it's not shared on the room.
I see.
Yeah, sorry. The room will not see these slides. Yeah, sorry.
Okay. I think we have a little bit of a problem. Now it's the. All right. So it's a pleasure to be here giving this talk, although I'd rather it wouldn't be happening now, maybe in 10 years. But this is the end. This is my farewell performance. And I'm going to be touching on things that happened for more than 50 years in my career as I became a spectroscopist and learned what we can do with spectra. Okay, this is interesting. I don't want to do that. I'll look at it. Maybe I should just use my.
Does it have to be that high?
Yeah.
Can't you move the whole thing down?
Well, that's out of my knowledge of this project. But,
Yeah. It's like,
My computer, it just means that it's going to be a little bit farther away.
That's fine, I think, yeah.
Okay,
okay.
so. Since I'm not a physicist, I start with molecules. And the simplest molecule is a diatomic molecule. And when we approach a diatomic molecule, we can't do anything until we see patterns. And so this is a talk about patterns and then how they break and how we see patterns among the broken patterns. And then maybe some more iterations. So the first section is about diatomic molecules. And then we take the big step to polyatomic molecules, which are incredibly more complicated. And for some people, more interesting than diatomics. But my love has always been diatomics, and so I keep going back to them. Then I will have something political to say about adiabatic versus diabatic potential curves. Because one is something that we can know computationally, but there's no insight there. But the diabatic picture gives us insight. And the diatomic picture is often hidden because we don't calculate it directly. And so I'll show how that works. And then I'll talk a little bit about geology or the state of the universe or whatever. We have oxygen on Earth, and we didn't always have oxygen. And so 2.5 billion years ago, the atmosphere started to have oxygen. And that profoundly changed everything. And there's a record of the great oxygenation event that occurs in minerals, which is the ratio of isotopes of sulfur. And people know that that signals the GOE, but they don't know why. I'm going to tell you why. And it's all going to be spectroscopic esoterica. And then the final topic is when you do photodissociation of a molecule, it's a sudden process. The molecule is well behaved, well known before you hit it with a photon, and then it falls apart suddenly. And how do you know what the transition state is for this photolysis? Textbooks tell us you can't learn about transition states by spectroscopy, but you can, and I will. And the last topic will be a review of some of my most important people in my career. Okay, so for a long time, I worried about what's more interesting, structure or dynamics. It doesn't take much effort to say, well, structure is simple because nothing's moving and you can measure it accurately, but dynamics is a more complicated thing. So, but then as a spectroscopist, I observe energy levels, and energy levels are sharp. And normally the simplest idea about dynamics is something gets broad, the uncertainty principle. So if something's happening, the levels get broad. And that's not true. The code of dynamics can be encoded in a broken pattern of patterns. And so I'm going to be talking about quantum cryptography, which seems like a strange sort of thing. But since the main topic of my talk is pattern breaking, and I insist that that is where you learn about dynamics. And of course, all of this started when I was a graduate student, and I decided to study perturbations in the CO molecule. And I didn't know why. I just thought they were interesting. And for a long time, I thought, well, I was studying other people's garbage, which is an interesting thing because there's not much competition there. But so I didn't know what these pattern breakings were good for, except I was curious about them. So in spectroscopy, everything depends on being able to perceive patterns in the spectrum and to extend those patterns. But then sometimes they're broken. And Hertzberg, there used to be a story about Hertzberg that when he encountered a perturbation, he put the information about it in a drawer of his desk, never to be looked at again, because the perturbations don't get put into big tables of multi-digit numbers. But I'm interested in, what do molecules do? Why do they, what are molecules thinking? And why do they do what they do? That's sort of a kind of psychiatry. So I'm a molecular psychiatrist. Okay, here's a pattern. The top spectrum is very simple looking, and it's a well-behaved band of sulfur oxide, silicon oxide. And you can see, anybody here can see that there's a pattern there. That's the p = 0 level of an electronically excited state. The lower spectrum is the v = 1 level. That looks kind of messy. Now, some of you see fragments of patterns and say, well, I ought to be able to work into the nitty-gritty, but it's an awful lot of broken stuff. It turns out that breaking is due to one perturbation parameter and one electronic state. There's basically two things you need to know in order to recover the information in the simple pattern. Okay, now this is the only equations in the talk. This is the two-level problem, and we have two kinds of levels, bright states and dark states. Bright states are bright because they're connected to the ground state or to the state you're using by an allowed transition, and dark states are dark because they're not. And the dark states perturb the bright states and make themselves known to us. And so this is the equipment we use to interpret perturbations. And so we have language called level shift, intensity, borrowing, extra lines, all that sort of stuff. It's all explained by this simple two-level problem. So we heal perturbations with these simple set of equations. Okay, now patterns, as you can see, as you saw from the previous slide, are multifaceted. There are several things about the pattern. There's rotational branches in the spectrum. There's vibrational bands. There's electronic states. There's fine structure of the electronic states. And there's transition state selection and intensity and selection rules. So those are the things you need to know to deal with the spectrum. And they're not all the same. And then perturbations, they also are multifaceted. They have selection rules, there are extra lines. There's patterns of multiple patterns, patterns of multiple crossings. There's isotopic substitution, and all of this can be dealt with by having perturbation matrix elements, which depend in a predictable and usable way on either calculations or simple energy level formulas. Okay, so here's a collection of perturbations. It's in silicon oxide, not carbon monoxide, but I'll accept that as a good substitute. And we have two, we call it a Christmas tree diagram. It's kind of a sick looking Christmas tree, but all the perturbations that are observed in SiO are on this diagram. And what you see is there's some different colors of points, different shapes of points, and there are groups of 3, groups of 1, and each electronic perturber, each kind of electronic state perturbs in a certain way that's recognized. And also there's multiple vibrational levels that perturb. And so by harvesting the information on this, we find the name and structure of all the dark states. Not supposed to be possible, but routine. So here we have a situation where we have broken patterns and they're arranged in a pattern. So we have a pattern of broken patterns. And that determines the symmetry of the state. And there's more details here, but we don't need to see them. Okay, so nature can be kind. It's like in the Haslam breadcrumb trail. If you know what you're looking for, you can survive. And now the perturbation matrix elements are something electronic or something physical times some overlap integral, which is easily calculable. So there's always 2 parts, 2 factors. And using the 2, we can make progress of understanding these. Now there's something also that's really neat. If you have a perturbation, the vibrational factor that controls this perturbation, the strength of the perturbation, is an integral, a vibrational overlap integral. And that integral accumulates at the internuclear distance where the 2 curves cross, not at the energy of the crossing, but at the internuclear distance of the crossing. So all you really need to know is where do the curves cross? The matrix element is determined there, and quantum mechanics is sometimes local. Even though we're told in all the textbooks, you always have to integrate over all space, but it's local. And all sorts of insights occur when you have that. And it's like classical mechanics. Okay. So now we're starting to go into the dangerous territory, going from diatomics to polyatomics. For a diatomic molecule, each electronic state has 1 vibrational mode and 1 rotational constant. An N-atom polyatomic molecule has 3 rotational constants and 3 N-6 vibrational modes. So one consequence of this is that in a diatomic molecule, you see perturbations mostly between electronic states. But in a polyatomic molecule, there's all sorts of perturbations among the vibration levels of one state. Now, this may not be interesting, but if you want to know about molecular dynamics on one electronic surface, that's the whole story. But there are rules, really fantastic rules that describe all of the matrix elements among the vibrational levels. And these rules are based on insight. So here's this word, polyads. Polyads are a group of near degenerate vibrational levels of one electronic state. And these vibrational levels interact via the anharmonicity. Now, anharmonicity is something we like to avoid, but it's the whole story for polyatomic molecules. It's not just that one mode is anharmonic, but the interactions between them are anharmonic. And these interactions tell you something tremendously important about the structure and dynamics of this molecule. And it turns out there's all sorts of simple rules that enable you to do wonderful things with the vibrational structure of the polyatomic. So we have a speaker tomorrow who's going to talk about that. I'm going to have a thing or two to say about this. But anyway, what's really important is resonance. If there are two modes which have the same frequency or an integer multiple frequency, or if there are three modes where two of the frequencies add to the third, if there are simple integer relationships between the normal mode frequencies, we have what's called resonance. And instead of having a local perturbation, you have something that scales and that is really wonderful and important. And another thing that you sort of expect in a polyatomic molecule is the normal modes, which involve two or three of the same atoms, or two bonds, or one bond. Those are going to have the strong anharmonic interactions. And so, even though you might have 30 vibrational modes in something like benzene, I didn't do the 3n-6, but I think it's right. There are only some modes which you think are going to interact strongly, and you better know about them. And they're going to present that information to you in a way that's easy to understand. And if you then have a polyad Hamiltonian, you know all of the dynamics, or at least all of the fastest dynamics, which is really all you really care about, because if it's too slow, you don't have, your experiment is never going to get you. So in polyads, we have an incredibly rich set of patterns. We have two really important kinds of resonance interaction. One called the Fermi interaction, which is between two modes differing in frequency roughly by a factor of 2. Roughly is really an important word here, because it's not just a factor of 2, but and the higher up you go, the less problem there is that the frequencies are quite integerable. And we have Darling-Dennison, which is the really important, which is when you have two modes which have roughly the same frequency, but have different symmetry. And so it has to be a 2-to-2 resonance rather than a 1-to-1 resonance. And this leads to local modes. And local modes need to lead to isomerization, because most of isomerization is one atom moving from one place to another. And so instead of having all of the atoms moving in a complicated dance, one or two do something, and that pops out of the polyad picture. Okay, I don't want to go well. So the polyad Hamiltonian is something that's really wonderful, because once you observe the lowest member of a polyad, lowest example, then you can extrapolate it up in energy, because all the matrix elements that are important scale in a predictable way with the quantum numbers. And even more importantly, the membership of this polyad scales up in a dramatic but completely understood way. And so what ends up happening is the polyads dominate state space. And we already know what each polyad is doing as you go up to higher in energy. And now you say, well, let's see whether something interesting happens. Because we got a pattern, a complicated pattern, which is explaining everything. So we go until it breaks. When is it going to break? When the molecule breaks, or when the molecule isomerizes. Now, if you're hiking and you need to, and you need to get help from people that you encounter on the trail, and you're crossing an international boundary, you aren't going to get any help from the people on the other side of the boundary that speak the other language. And it's the same thing with the polyads. Okay, now we're going to talk about acetylene, which aside from CO is my favorite molecule. And those are the normal modes of acetylene. And what you want to notice is that there are two modes, modes 4 and 6, which have nearly the same frequency. And so these two modes are going to interact strongly because they're resonant. And acetylene is small enough so that they're not going to be able to hide from each other, even though they're not the kind of interaction we really want to see. We would like to be able to see the cis-trans isomerization of the excited state of acetylene, which is transbent. And so one normal one is a transbending mode, and another is a cis-bending mode, but they don't have the same frequency. Instead, we have a resonance between the cis-bending mode and the torsion. And well, that could be interesting, but not in terms of making the cis-trans isomerization. So, but we have a polyad, and we're going to look what happens. What happened? Why is it not? Okay. So here is a summary of all of the vibrational levels of the first excited state of acetylene up into the top of the barrier to isomerization. This has never been done before for a 4-atom molecule. And you might say it's kind of a waste of time because it took roughly 50 graduate years of research to fill that out. But you know, there's something valuable. Now there's several circles around the symbols with B2. There's B2 by itself, there's B2 with 3,1, B2 with 3,2. And mode 3 is the transbend. And we want to get cis-bend and transbend together to make local benders. So we have polyads between modes 4 and 6, which is not what we're interested in. And so this polyad between modes 4 and 6 should not care about the number of quanta in non-interacting modes. And so as we add mode 3 to modes 4 and 6, we expect to see a spectrum, a pattern repeating, but it doesn't break. And why does it break? Because modes 3 and 4, 3 and 6 want to make a local bend, which leads to isomerization. So by looking at this kind of data, we can determine the structure of the transition state. Something the textbook says high resolution spectroscopy or discrete spectroscopy, eigenstate spectroscopy can never tell you anything because a molecule samples the transition state for a fraction of time, a period of time roughly equal to the fastest vibration mode. So anyway, we look at this and we see that there's something happens, the polyad breaks, pattern breaks. I told you before that the information about dynamics is encoded not in a broadening of levels, but in a pattern that extends over a certain distance. So we are able to determine the isomerization path. And one of the things that is really interesting is that it goes back to classical mechanics. if you have a barrier in a problem, in classical mechanics, when you go to the top of the barrier, you have a stationary point. Well, quantum mechanics can't do that, but it gets close to the top of the barrier. And so what you have is a dip in the frequency of a mode. And that dip tells you everything. So we determine from analysis of the spectrum that the shape of the potential, the shape of the barrier, the height of the barrier, the difference in energy between the two modes, minimum, we get everything. Not supposed to happen, but some textbook writers don't think, they just write. Okay, now I like to speculate. Normal modes involve a many atom kind of choreography. As you get more energetic and more excited, eventually the dancers are just going to get completely exhausted or out of phase. But nature fixes it so that many atom choreography breaks to leave a pas de deux, where two atoms do what they want. And this is what we're seeing. So you're going to, we see isomerization, and we recognize it by a large amplitude motion along the minimum energy path. And we get that from analysis of the polyhedral spectrum. Okay, the next topic, the diabatic picture versus the adiabatic picture. Now, if you're a quantum chemist, you calculate adiabatic stuff. You have computer programs that tell you what the shape of a potential curve is, and you have a tool which enables you to determine that as accurately as you want. Now, molecular orbitals are an incredibly bad basis set. You have to use millions or billions of them to describe a potential surface accurately. So you get the truth, you get the potential surface. It's computationally accessible. You can get to whatever accuracy you want. But you get very little insight about what the molecule was thinking. So, a simple example. An example that I've taught many times, but incorrectly, in introductory quantum mechanics courses. The carbon dimer, C2. This is a molecule with 8 valence electrons. It's electron deficient. But we use it to illustrate the LCAO, linear combination of atomic orbital, molecular orbital theory for molecular structure. And so there's predictions about C2 and N2 and O2 and CO and CN, and all of them based on these same ideas. But what I'm going to tell you about is not in that lecture and not in that topic at all. So the molecule knows what it wants to do, but it doesn't tell you. It doesn't tell you anything what's behind the adiabatic picture, except that the potential energy you calculate curves that you calculate are deformed. They have all sorts of large and small strangenesses. The diabatic picture reveals everything. It explains all of the strangenesses. The diabatic curves are simple, and they cross through all of the diabatic curves and lead to avoided crossing and stuff like that. Anyway, so I'll show you. Now, first, this is work by a former graduate student who was also a former postdoc and now an independent scientist, and he didn't do this with me. He did it on his own. C2, the C singlet pi state of C2. Looking at the vibrational energy differences for the vibrational levels of this curve, of this state, the vibrational energies differences behave badly. Now, you might say that the curve on the left doesn't look bad. Well, it's not supposed to happen. It's supposed to be almost constant, with a little bending over at dissociation. Well, what happens is, in this state, the molecule is trying to go to the correct dissociation limit. But it can't, because it has to cross with all sorts of other stuff. So it goes to the lowest. And we can understand all of this by the concept of valence hole. Now, when we do for homonuclear molecules, LCA-LMO theory, we normally think about the two atoms, the two separate atoms always being in the same electronic state. But if one of them is in a highly excited state where there's an orbital, an s orbital missing, which goes to make an antibody molecular orbital, then we get something where there's this class of states, or a very small class of states, one valence hole state that goes through and explains everything that's bad about the potential curves. And you can see, if you look at this carefully, you see some deformations, but let me show you more precisely. The circles are showing places where the diabatic curves cross. And this leads to peculiarities in the adiabatic curves. It's also true that where there is mixing between electronic states, you have chemistry and collisions. The collisions are very good at changing electronic states or doing a reaction when you go to one of these special places. Okay, now this isn't just one state of CO, this is 4 states of CO. And you can explain all of the weirdnesses for all 4 of these electronic states. And you can also do this for N2 and CN and NO and CO. But the neat thing about C2 is all of this weirdness is down relatively low where the experimental information is complete. But JJ has explained a lot of this stuff in terms of this valence hole concept. Now, as I said, there are strange things happening when you have an electronic state, you think it's bound, but it's in the region where the lower state is dissociating. It's interacting with the continuum of the lower state. And so you can do a calculation. You can find the rotation and vibrations and electronic state dependence of the lifetimes by having one continuum and a bunch of bound states. It's a simple calculation. And I used to teach that in 573. Not anymore. Okay, you can see that each of these curves, each of these spikes is due to an interaction with a particular electronic state. And we explain, we can get the lifetimes of all of these states from this calculation. Okay, now there's another really neat thing about C2. C2 is seen in the spectrum from comets. And 80 years ago, Hertzberg said, this is really strange. The head of the comet is green, the tail is not green. And he knew what the green was, the swan bands of C2. And some clever people like that, the swan bands, and they named another band system, the duck bands. Swan was a person, duck is not a person. But this is not the story. Hertzberg had an explanation which involved spectroscopic esoterica. Solar radiation destroys all of the C2 in the tail. So the green is gone, but solar radiation also excites the upper state of the swan bands. And so while there's still some C2, you get green. emission, and after it's all burned away, because there isn't a massive source of it, it's just gas phase C2 trying to make an escape. Unfortunately, we can't do it. Anyway, so Hertzberg was right 80 years ago, but he couldn't do the experiments, and he couldn't do the theory. And it's another case of putting something in the drawer. I don't know if he did that. But anyway, now I'm on my last. No, I'm not. The next to last topic. The great oxidation event. We know that life on Earth depends on oxygen in the atmosphere. And before there was life, there wasn't any source of oxygen, and some primitive forms of life started to do stuff, and they generated oxygen. And eventually there was a lot of oxygen. And one of the things that oxygen does is it absorbs in the UV and in the vacuum ultraviolet. In fact, that's why we call it vacuum ultraviolet. So for a long time, we knew there was such a thing, and we knew when it occurred. And the main evidence for the GOE is isotope ratios of sulfur in minerals. Now, minerals are not in the gas phase, nor are drugs. And I don't study anything that's not in the gas phase. But we can explain the change in isotope ratio of sulfur in minerals and explain why the GOE is responsible for this change. And I think that if one looks at the isotope ratios that were in minerals from different parts of the Earth or that were deposited at different times, we can sort of know whether we, maybe not such high resolution, but anyway, we learn about that. So we're going to talk about isotope ratios. And the elements of the discussion is permutation symmetry of identical nuclei. Something that even spectroscopists don't know much about and don't want to know much about. But it's there if you have two identical nuclei and they're either bosons or fermions, and there's some restrictions on which energy levels can exist. And the S2 molecule, the sulfurs are bosons, half the rotational levels are missing. That's an important factor. Then there's two electronic states of S2, much like that are important, much like the two most atmospherically important excited states of oxygen. A triplet pi state and a triplet sigma state. The triplet sigma state is bright and the triplet pi state is dark. They perturb each other by spin orbit. So we have now spin orbit perturbations and nuclear permutation symmetry, two favorite esoteric topics of small molecule spectroscopy. And from this, we're able to show why the GOE is signaled by isotope ratios. Why is that? And Alex Hall is the one who did this. He made these figures too. They're really neat. So we have a volcano, and among other things it belches out is H2S and SO2. And these two gases are processed in the atmosphere, and eventually they get embodied in minerals. And we have a reduced form of sulfur going into pyrite, and an oxidized form going into barite. So before the GOE, there's no oxygen, there's no ozone, everything is exposed to extreme ultraviolet, and all sorts of stuff happens. And so the H2S and the SO2 are atomized, they're torn apart. And eventually the atoms find each other and form gases, and the gases either rain out, anyway, they get embodied in the minerals. But the neat thing is that the pyrite is sampling sampling the reduced form of sulfur and the oxidized form. And so something is happening in the atmosphere as the sulfur comes down. And so here's, so the reduced form of sulfur, you start with S2. In order for S2 to form, there has to be a three-body collision because the two sulfurs come together. So it makes S2, and then once you've got S2, you can go down the path. And UV light is not friendly to any of these guys. So there are two excited states of S2. One is short-lived, it radiates, decays by radiation. The other is long-lived. And so it can only borrow some radiative strength from the other one by perturbation. And so you can see now that these two paths can interfere with each other or can compete with each other. And in fact, that's what happens. So the model that Alex Hull developed for this involves looking at all of the known vibrational levels of the V and V prime states and all of the perturbations between them. So we have a set of more than 19,000 rotational vibration levels. And every one of them, we know the fraction to lifetime. And then we can make a model that says, well, the long-lived states are going to be hit by UV radiation, and the short-lived states can escape. And it takes the process by which the separation occurs is very weak. But we got a long time, and we do it again and again, and eventually you get this isotopic fractionation. Okay, now I'm on the last time. I'm probably way over time. I've never given a talk that has ended on time. My last one is not going to be one. Okay. Photolysis of vinyl cyanide. What's the transition state? Or maybe there's several transition states. And we are going to look at the transition state of the photolysis of vinyl cyanide using a technique that was developed by Brooks Pate, but exploited very much in my research group, Chirpulse millimeter wave spectroscopy. But the really neat thing is what we're looking at is two of the fragments, HCN and HNC. They have rotational spectra that are at fairly similar frequency, but profoundly different rotational constants. And so we can measure the rotational spectrum of HCN and HNC that are formed by photolysis. And what we see, we look at, say, the J equals 0 to 1 transition. All vibrational levels have similar rotation constants. So we have what are called vibrational satellites. So we're getting information about the vibrational population distribution from the rotational spectrum. This seems counterintuitive because vibrations are big, rotations are small. But the problem is vibrations being big requires a lot of spectrum. And vibrational bands have to be disentangled. And but the rotational spectrum is very simple because it's diatomic molecule. So we can obtain information about vibrational population. Now, there are three structurally distinct hydrogen atoms in vinyl cyanide. And so we could modify the parent molecule by doing isotopic substitution, deuterium for hydrogen, at each of the sites. And that's neat, because now we're sampling the transition state or transition states by three different ways. And we have the microwave spectrum of HCN, HNC, DCN, and DNC. And they have the vibrational satellites. And so we can tell what's going on. So before people knew anything about photolysis of vinyl cyanide, they made a simple hypothesis about what the transition states would be. One was called the 3-center path, and the other the 4-center path. Now, that's just a good guess. It was not based on any calculations. It was just based on what people knew about how molecules could summarize. And you can see on the top, I think I better die. You see this, there's the 3-center path that this hydrogen comes around and bonds to that, and then that leaves as HCN. The 4-center path is here, and you can see it's. Oh, there it is. There's 4 centers. The N goes around and grabs the first hydrogen. And then what that generates is HNC. And it also generates the C2H2 fragments are different from the two paths. And I was hoping that one of them would be accessible, because I've been trying for the last 15 years to see the spectrum of vanillity. Unsuccessfully. Now, if I were giving this talk 10 years from now, if I were still alive, I would have seen vanillity. So the spectrum that Hiro Rosemed observed shows more than 30 vibrational levels of HCN and HNC. That's really amazing. And these are all vibrational satellites of the J equals 0 to 1 transition. And we can assign them all. And I won't bore you with that. That's not trivial. And there's even hyperplane structure. Okay, so this is the raw spectrum, and we can then look more carefully at it by doing the isotopic substitution. So we can replace one of the hydrogens by deuterium. And that, if you remember a couple of slides from before, it would shut down one of the paths. It would shut down the 3-center path. And so the product of the it would shut down the 4-center path. The product of the 4-center path of HNC. And so substituting that hydrogen should turn that one off. It doesn't. It reduces it by 10%. So it tells you that these two naive pictures about transition state are a little too naive. There's more going on. If we looked at all 3 of the hydrogens individually separated, we would have much more insight And I think that a complete picture of the transition states would emerge. So, is it still true that transition states are not experimentally true? Okay, now I want to talk about some of the important people in my life. This will be quick. When I was in college, I had a summer job at Argonne National Lab, and I was looking at spectra of antimony pentafluoride in anhydrous hydrofluoric acid. And I was looking at the NMR spectra. I got beautiful spectra. And my boss, Herb Hyman, told me, okay, now create a model for this spectrum. One model. Like the spectrum, I thought that was the whole story. And that was really an important thing. And then went to Harvard and worked for Bill Klemperer. And Bill was a really special person. And there are many stories I could tell, but I'll just do this one. He would come into the lab and he would, sometimes he might pick up a screwdriver or a wrench and start sticking it into a high voltage power supply. We had one person who always was on Klemperer patrol, but that's not what happened. He would say on some subject that either he or the graduate student proposed, he would say either I'll bet you $1 million or I'll bet you a nickel. And when he was betting a nickel, he was absolutely sure. And he didn't care, he couldn't collect $1 million. He certainly could collect the nickel. But it was the kind of humor and excitement that he had, which I hope I conveyed to my graduate students. And the curiosity, I'm not going to tell them what's right and what's wrong, but we'll play a little game. Then, as a postdoc, after 6 years in the Klemperer group, trying to make a particular experiment work, which was looking at the transition between lambda doublets in the CO single pi state in order to measure the electric dipole moment of that state. Six years, my experiment never worked. I went to Santa Barbara. Emeritus said, was one of my two supervisors, said, why don't you look at barium oxide? And why don't you excite it with a particular line of the argon ionizing and see if you can see a microwave spectrum. Now, he and I knew something about that. That experiment worked in 2 weeks. And I thought I was really hot shit. It turns out that Rita and a previous postdoc had identified this wonderful possibility for doing microwave optical double resonance on barium oxide. And Herb knew exactly what was going to happen. And it did. Then there is the book about diatomic molecule spectra and perturbations, which I wrote with Elliot Lefebvre. Well, I can tell you stories about working for a long time with another co-author, and it usually doesn't end well. But we produced this book, and it is really everything you need to know about diatomic molecule, and it's been recognized as that. So I came to MIT, and I'm the only person I know who was interviewed twice for a job in the chemistry department at MIT. I did not receive an offer after the first one, but at an Air Force Office of Scientific Research conference, that happened to be in Santa Barbara, Jim Kinsey came up to me and said, would you be interested in a second interview? And I knew I was, and I was successful. And it took about 10 years before I started collaborating with Jim Kinsey. And we were profoundly different in terms of the kinds of questions we asked and our style of research. And so we learned an enormous amount from each other, and it was an incredible relationship. And I think he is maybe competitive with Klemperer in terms of how I came out. There's Bob Silk. Kinsey had the bad taste to lead MIT before I was done with him. And so I ended up collaborating with Bob Silverman. Now, Bob is really special, was really special, because if you talk to him for 5 minutes, he gave you the idea for a paper. For 15 minutes, he could produce the idea for a PhD thesis. In an hour, he could produce the idea behind the entire career. And he did this in physical chemistry and many other things. And there are many people who are lining up to have at least a 5-minute and probably a 1-hour conversation with him. And he had a tremendous impact on MIT as a result. Finally, MIT students are incredible. And I had 58 PhD students, and I learned an enormous amount from them, much more than they learned from me. So thank you.
Questions for Bob? Comments?
I won't bite.
Everyone is in awe.
What about all the topics you left out?
Well, there were a lot of them.
There were a lot of them, yeah. Sea land, for instance. Anyway.
And there's Mike.
And there's also Mike McCarthy. RFs.
I think that's too broad
Question.
a question to
Go ahead.
respond to.
Impossible to answer.
But there were 58 students, and they were all smarter than I was, and so yeah, we did a lot of really good stuff. Come on. The talk is supposed to stimulate questions, not stun silence. Yes.
What molecule is taught you the most?
Acetylene. Acetylene.
Because it's polymer.
Early. You know, two hydrogens. Many people would say that's really a diatomic molecule, whether it's C2 or H2, but it's yes, but acetylene. I also tell a story early in my career when I first made the transition to polyatomic molecules. There were two, formaldehyde and acetylene. And every experiment we did on formaldehyde was successful, but unsurprising. Every experiment we did on acetylene was successful, except for vanillin, and very surprising, and really taught us a lot.
What about calcium halide Rydberg states? There was a lot of surprises there, weren't there?
Yeah, okay, so we could talk about multi-channel quantum defect theory. I don't want to do that because that would take too long.
Yeah.
But I could say something about the electronic structure of molecules which are very ionic. And so calcium oxide is my example. And the electronic structure of calcium oxide is really simple. But it was so complicated that there was a famous spectroscopist who said the orange and green bands of calcium oxide can't possibly be those of a diatomic molecule. But they were, and we understood them completely. But the ground state is calcium 2+, 2-, O2-. All of the excited states are calcium 1+, O-. Now, calcium 1+ is like sodium 1+, and O- is like fluorine. And so calcium fluoride and sodium oxide spectra, I didn't do anything on sodium oxide, but that was the model for understanding calcium oxide. Now you take one step from calcium oxide, which you understand perfectly in an intuitive model, not a computational, not a quantum chemical, but a model that explains all of the details of this spectrum. Scandium oxide. It's horrible because the 1+ scandium has a d orbital and an s orbital. And there's a lot of states. And now inorganic chemists know about ligand field theory. And they know how to deal with ionic molecules. But diatomic molecule spectroscopists and theorists don't. And I said earlier that molecular orbitals, which we love, and which organic chemists are especially fond of, are an incredibly bad basis set. Whereas atomic ions, all the atomic ions, you have tables of energy levels and assignments and fractional characters. And the atomic ions, you don't need quantum chemistry. It helps. And so you have a wonderful picture. And now you take two atomic ions, which have completely described electronic structure, and you bring them together. And one acts as a point charge to the other. And if that's not good enough, then you have some multiple moments and all sorts of other stuff. And so you have a theory which is going to capture all the important stuff. And now you go from calcium, from scandium to the next one. And now you have 2D orbitals. So that's 45 degeneracy times whatever. So you get huge numbers of electronic states. But you can get the 2+ states for the next atom from the 1+ state for the previous atom. And you can use that to go all the way across the transitional series. So that's really what, a topic, electronic structure of transition metal oxides that I really think, and that's why I want Dan here, because I want to convince him that he can do calculations using atomic ion basis sets, and that we can all learn from the inorganic chemists too. Okay, that was a very long answer. Yes.
What's the deepest mystery that?
I don't go to the deep ones, I go for the shallow ones. I think that I really have to ask that question.
Anything further? One closing comment, which is, I think, all of us on the faculty echo, is how much more we get out of our unbelievable students than how much we are ever able to put in. And this is something that just, for, a lot of the students here, you don't realize from day-to-day activity how unbelievably awesome you are. But we do, right? And so it's just this MIT gift that keeps on giving, and it will continue. That's the one thing I'm most confident of. So thank you, Bob, for so many things.